Hey everyone, so this is going to be the last topic of this Regents Physics course, which is all about modern physics. So I had mentioned before that everything that we've learned so far is based off of Newton's three laws. In fact, it's typically called classical physics or Newtonian physics because every equation can pretty much be brought back to that. It turns out though that near the early 1900s, uh, scientists started to get better technology, better measuring devices, and we started to realize that things didn't really fit like they should based off of Newtonian physics. And that led us into what we now call modern physics, where it starts to get a little bit hairy as we look at the extremes. So, this is basically what I just said, that we start to really realize just how deep and crazy the physics world can end up being. So there's two different parts of modern physics. It really and they focus on the extremes of the world and of the universe. For the most part, Newtonian physics and classical physics does work really well in the, I guess you could call it the human scale, what we experience on Earth and all that stuff. But whenever we go to either the extreme small or the extreme large, the rules start to break down. Now, it turns out that each of these major fields, the two extremes, was end up being pioneered by different scientists. So the first extreme was relativistic mechanics, which deals with very, very large objects such as planets, stars, galaxies, or objects that move very, very fast. And typically by fast, we mean near the speed of light. Now, this was pioneered by the scientist Albert Einstein. He's basically credited to this aspect of relativity and relativistic mechanics. Unfortunately, we're not really going to focus too much on that. I'm pretty much going to say it. The equations do get a little bit tricky, but they are really interesting because it leads into things called time dilation and length dilation. Things start to contract and get smaller. This also goes into the craziness of black holes and the whole infinitesimally small dense points in space. So, yeah, we're not really going to focus on this one too much. The other side of the coin is the very, very small, which is quantum mechanics. So, this is basically where we start looking at what's going on in the atom. So, like I said, we didn't really have the technology at the time to really know what's going on with the atom. But now at this point, we start getting better technologies, better equipment, and we started learning a lot of weird things. Now, this was pioneered by the scientist Max Planck, and this is where we're actually going to focus on with this course. Though I will point out that if you do any research about quantum mechanics, you do know that it is actually just as crazy as relativity. However, we're barely going to scratch the surface of it. We're kind of going to take a glossary overlook on it, but we will be focusing mainly on the quantum mechanics aspect. So this kind of shows the concept, I guess. You know how we have classical mechanics here, and when we look at very, very small objects, we go into the quantum mechanics. When we're looking at very, very fast or larger objects, it's relativity. And then one of the big aspects and the driving forces for scientists is to try and find a way to combine everything into one concept. So for now, relativity and quantum mechanics don't really mix well with each other, but scientists are trying to find a way to kind of combine them, and that leads into things like string theory. So, string theory is a way of trying to explain what happens at the very large and at the very small at the same time. All right, I'm going to try to breeze through this idea of the atomic model. So, as you all know from chemistry, we started off in the 1800s with the atomic model. John Dalton came up with essentially what we would consider like the Lego model, that there would be a small piece that atoms can be broken up into, combine together to make whatever you want. In the 1900s, we end up getting a little bit more detail about the atom by J.J. Thomas, um, where he actually comes up with charges, electrons, and protons and stuff. Though he actually believed that the atom was made up of essentially a positive C of charge, and then the electrons were kind of scattered around in there in the plum pudding model. Uh, Quick side note, it is really odd how very quick a lot of scientists are, especially back in the day, to assume that things acted as a fluid first before we kind of discovered how it actually is. A lot of scientists used to believe that surrounding the planets was what was called an aether, which was a kind of a planetary fluid. Electricity was considered a fluid that merged between things. Heat was considered a fluid. So it's really weird how the moment a new thing pops up, scientists immediately go to it's a fluid first before um, coming up with the actual thing. A few years later, we end up getting Ernest Rutherford, where he comes up with the gold foil experiment. As you probably know, he was actually trying to prove the plum pudding model, but he found some really, really weird results. Um, he expected that if he shot these alpha particles, which are just helium nucleuses, but if he shot them straight through the gold foil, he kind of expected it to go straight through, maybe a few deviations here or there, but for the most part, he kind of expected it to go straight past. So this was his expected results. But what he noticed is that a lot of them started scattering a lot more than he expected. And in fact, some of them even bounced back. He was quoted saying that it was as if he shot a cannonball at a piece of tissue paper and he saw the cannonball fly back. That's how shocking this was to him. So this told him that there was a very small and dense nucleus due to the fact that only a few particles bounce back, and that for the most part it was surrounded by an electron cloud, which is why majority of the particles were passing straight through. Uh, and this is what we normally use. This is the what we call the planetary model. He didn't really go into much detail about it. He just said that the electrons were floating around it. Um, but the problem was that if electrons are going around in a circle, that means that they're accelerating. And one thing to note is that charges that are accelerating, such as going in a circle, have to emit light. And if they do that, that means that the electrons are going to be constantly emitting energy. So in their orbit, they would start to lose energy through emitting of the light, which means that they would slowly slow down and start falling towards the nucleus. And essentially, all the particles would end up blowing up essentially within milliseconds of them forming. Since that doesn't happen, something was wrong with the model. And then this is where Niels Bohr came in. He comes up with the Bohr model, where the electrons have to be orbiting at very specific intervals. It's related to standing waves. I'm not really going to go into too much detail with that, but basically at these very specific intervals, the particles can orbit without technically emitting any light and being almost in a, I guess you can call it a equilibrium state. And then he said that electrons can start jumping between orbitals by either absorbing or releasing energy. So this is the typical theory that we're going to be using. Now, it turns out that this also isn't completely correct. They don't orbit at these flat levels, but more again in a cloud. And these are just high probability areas. Electrons can exist in between, but again, not going to go into too much detail. The Bohr model ends up being the more easy to use setup. Now, this goes into something that I need to mention really quickly, which is particle theory and wave theory. So, scientists can come up with two different descriptions where we can consider objects to be particles or objects to be considered waves. Particle theory essentially are phenomena and descriptions that really only work for particles, and wave theory are things that only really work for waves. So you can kind of think of when you think of particle theories that these are things that humans, tennis balls, planets, atoms, they can all experience. While wave theory would be something that only like water waves or sound waves could do. So these are a bunch of phenomena, and you kind of need to know which ones are representing particle theory and wave theory. So for the most part, collisions and momentum are strictly particle theory. We actually mentioned that waves can't collide. Momentum is something that's about collisions, particles hitting into each other and bouncing off and going off in different directions. Waves don't actually do that. When waves collide, they transfer their energy through each other and they end up interfering. So waves actually don't do momentum. Reflection, that's actually something that's explained by both particle and wave theory. You know, both tennis balls reflect and sound reflect. So that's not really something that you're going to see too much in a, which one's wave and which one's particle. Refraction's also something that can be exhibited by particles and waves. I mean, we saw light waves in particular, particles. That would be something like pushing a cart or a car towards a surface where the road is grassy or there's dirt in it or something, or maybe even a patch of ice, and noticing that it's going to bend differently. So, refraction does happen with particles. Diffraction is something that's only wave theory. Particles do not diffract. Uh, Interference is only wave theory. Polarization is only wave theory, and Doppler effect. So these are a list of particle theory and wave theory phenomena. Now, what ends up actually birthing quantum mechanics and quantum physics is this weird experiment where we started finding that there were materials that were photosensitive, and that if we put them in a circuit, they would actually create electricity flowing through. This is called the photoelectric effect. Um, and they noticed that instead of it being related to amplitude, like most waves would be, it turned out that the uh, electrons would be emitted from this photoelectric material based off of frequency. Um, and this actually said that light energy was based off of its frequency instead of its amplitude, like other waves. So this like started kind of getting scientists realizing that light isn't as what we would assume. Quick side note: as I said, this is kind of the birth of quantum mechanics, and this kind of led into it. Uh, Ironically, the scientist who came up with the photoelectric effect is Albert Einstein, and he actually got a Nobel Prize for this. And this is actually interesting because the concept of relativity that he ends up going into completely contradicts, or at least as far as we're concerned, contradicts quantum mechanics. So he actually didn't like quantum mechanics. He said it was too random for his taste. So it's kind of interesting that he ended up creating the field that he hated the most. Um, so as I said, this kind of started scientists realizing that photoelectric effect isn't, well, the light itself isn't really just a wave, and this photoelectric effect actually would be better explained using particle theory rather than wave theory. This actually led scientists to call light a photon. So you can think of photons as being almost like light particles or packets of little light. Quantum of light, that's actually where the word quantum mechanics comes from, as in discrete packets of light. Um, so you can think of photon as being a light particle. Um, Now, with the Bohr model, Max Planck actually did end up coming up with a relationship between the energy of a photon and its frequency. And it turns out that it's given by this equation. So E equals HF, which can also be rewritten as E equals HC over lambda. Because V equals F lambda, so we can rework that to substitute in the frequency. So this equation is what we're going to use. H is called the Planck constant. It's on the reference table. On the very front, it is given as 6.63 times 10 to the negative 34 joule seconds. All right. For the most part, it's going to be a pretty standard plug and chug. So you put your frequency in, your speed, your wavelength, your Planck constant, you get your energy. So let's work on this question. Pause video, work itself, and we'll go over in a second. All right. So for part A, to calculate the energy, we use E equals HF. We plug in the Planck constant as well as the frequency that they give us. Calculate it, and we get 3.63 times 10 to the negative 19 joules. You'll notice that most of the time when we're doing these, they're going to be very small amounts of energy. And then the color associated with this is going to be green. So you look on the reference table, you look for this frequency, and you see that it's going to be in the green range. Uh, Really quickly, don't forget that when we say color of light, it does not necessarily mean visible spectrum color. It means the entire spectrum. So if you had frequency at 10 to the 15th, that would be the color ultraviolet. So just wanted to throw that out there. All right, here's the next question. Pause the video, work stuff. We'll go over a second. All right, here they want us the particle of an alpha particle, the charge of an alpha particle. As I mentioned, the alpha particle is just a helium nucleus, so it's 2 protons, 2 neutrons. Only the protons actually carry charge. So I'm just going to do 2 times the charge of a proton, which, if you recall from the electrostatics unit, was called the elementary charge. So 2 times the 1.6 number, and you get 3.2 times 10 to the negative 19. Now, this question might seem like it comes out of nowhere, but this number is actually extremely important. So you want to keep that in mind. Here's the next question. Pause the video, work stuff. We'll go over a second. All right. So again, this time they want the wavelength. So we're using the form of the energy equation that deals with wavelength. Plug the numbers in, and we get our wavelength to be 6.1 times 10 to the negative 7 meters. All right, here's the next question. Pause video, work itself, and we'll go over in a second. All right, so they want the graph that represents energy versus photon frequency. So because the equation's equals HF, that means that there's going to be a direct relationship between frequency and energy. As the frequency goes up, so does the energy. So the answer is 3, the only one that represents a direct relationship. All right. And now there was actually one more experiment that showed how weird light was. I don't think you're really going to see the word come up. It's called the Compton Effect. This one was where they took X-rays and they actually bumped them into particles, and the fact that the light rays were actually able to interact and cause particles to move ended up showing that the light rays actually did have momentum. So this was another experiment that kind of led more credence to the idea that light could be considered a particle as well as a wave. And as we said before, momentum is really a particle theory type scenario. It turned out that the equation to find the momentum was given as P equals E over C. Now, this is not an equation that you need to know. It's just something that I'm going to mention briefly in a second. But for the most part, this was what they ended up finding. Now, so both the photoelectric effect and the Compton effect showed that light can be described as both a particle and a wave, which leads into the idea of something called the duality of light. That light is not just a wave, but also a particle. And it kind of like stands between these two states that we would normally consider completely different. So as we mentioned, momentum is given with light by this equation, E over C, which could also be rewritten as H over lambda. And it also turns out that particles have momentum too, right? P equals mv. All of a sudden, a scientist noticed this, that light has a momentum, particles have momentum equation. He kind of put the equations together, and he ended up realizing that particles have a wavelength. So he had a wavelength which he calls the de Broglie wavelength. And this is something that's true for all particles and all materials. Now, Before I get into this, this does lead into something really weird, that particles are also can be considered waves and wave motions. Uh, but the reason why we don't notice it is because the H term is so small that the only way to actually have the wavelength noticeable is to have the mass and velocity also extremely small. So this is something that we only see at the electron scale. And this was actually something that was proven, that electrons do have a wavelength. This is a question that if you wanted to, you could try out, see what it's like, and you would see that the wavelength for me is just, way too small. All right. So not only is light can be considered a particle and wave, but particles are also particles and waves. Uh, so this also leads into the particle duality as well. This was found, like I said, through electron diffraction. So, as we mentioned, only waves are able to diffract. The idea that if we sent a wave through a small little opening, it will end up spreading beyond the obstacle and kind of spread outwards in all directions. Uh, Normally, if we think about particles, if we sent them through these little openings, they should go straight through. No like bending, no spreading. But it actually turns out that they do spread, and they spread exactly like we would expect for waves. Uh, and this ends up proving de Broglie's hypothesis essentially. Now, there's three videos that I'm gonna link into the canvas. I highly recommend that you watch them. They're really short, and they really all kind of go into this idea about electron diffraction and what it looks like. And that's it. So, this is the first part where we just kind of introduce the idea of this duality of light and particles. Uh, so, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.